Okay, so far we've talked about where the signals in the NMR spectrum will appear based on the functional groups that you're dealing with, the type of oxidation states of the carbons to which those hydrogens are bound to. But now we're going to start thinking about some combo of type of splitting peaks that may show up in the spectrum that together can be utilized to figure out whether you have ethyl groups, isopropyl groups, terbutyl groups present in your molecule. And this will help you simplify the process of molecular identification a little bit more. So let's start by looking at a methyl group. Okay, so your typical CH3 group. If next door, so if you are looking at the carbons next door to where this methyl is located, if that neighboring carbon doesn't contain any hydrogens of its own, then the methyl peaks are simply going to appear as a singlet that will integrate to 3 hydrogens. But if the carbon next door contains 1 hydrogen, then the methyl group will be split into a doublet. Likewise, if next door you do have 2 hydrogens, on the neighboring carbon, then your methyl group is going to be split into a triplet. And if on the neighboring carbon of this methyl group you have 3 hydrogens, you are going to have just a singlet. Now this may seem a little bit counterintuitive. You may have thought that this will give rise to a quartet. But the thing is that if you do have 3 neighboring hydrogens on a methyl group, well, if you have a CH3 right here and next to you have another CH3, well, you got yourself ethane, and there is a mirror plane associated with the carbon-carbon single bond right here, because these CH3 groups are free to rotate. So right now I have it in the staggered conformation, but you could always draw this in the eclipse conformation and see clearly that you have a mirror plane. So what that means is that the CH3s on the left side of the molecule and the CH3 on the right side of the molecule are both equivalent. So you don't expect to see anything other than a single peak. And what this emphasizes is the idea that you have to be very much on point looking for those symmetry elements in your molecule, because if there are symmetry elements and you fail to account for them, you're going to end up predicting more peaks than there should be. You're going to start looking at the spectrum, not realize what the heck's going on. So do pay attention to the symmetry, right? Don't just go into autopilot mode and just say, oh, I have 3 hydrogens next door, I'm going to have a quartet. That may be true for some cases. In this specific case, that will not be true at all. All right, so yeah, that symmetry plane will do you in if you don't consider it. All right, now the methyl group, as I just mentioned, depending on what's next door, may show up as a singlet, doublet, triplet. But let's see what happens when we start bringing in more complex groups, like the ethyl group. The ethyl group is a typical substituent you could have attached to your parent molecule. So what's the deal with the ethyl group? Well, on the one hand, you have a CH3 group on your ethyl group that is next to a carbon with 2 H's. So the CH3 is going to be split into a triplet. But you also have a CH2 group, which is next to 3 hydrogens. So that CH2 group is going to be split into a quartet. And because the CH2 is only composed of 2 hydrogens and the CH3 is composed of 3 hydrogens, integration-wise, the triplet will be worth 3 hydrogens and the quartet will be worth only 2 hydrogens. And that's all you see if you have no other, if you have no neighboring hydrogens. But if next door you do have neighboring hydrogens, so for instance, this is technically a propane-like structure, but I've attached 2 R groups. It doesn't matter right now what the R groups are. But the point is that the ethyl residual fragment is next to a carbon that contains a hydrogen. All right, now for the CH3, that doesn't really change the picture whatsoever, because the CH3 is still bound to a carbon with 2 H's. So you will still see a triplet for your CH3. But for the CH2, the story has changed, because no longer are you just next to a carbon with 3 H's, you are also next to another carbon that contains 1 H. And so this will give rise to probably a multiplet. Now, the multiplet, the way this works, it really depends on the values of the J coupling constants. Um, if it's the case that one of the coupling constants is a lot larger than the other, then you're going to have something that looks kind of like this, in which case the first coupling constant is going to split up the peaks a lot, by a value a lot longer than the other, and then you might end up getting this kind of overlapping stuff. It's going to look almost like you have two triplets, but it's not exactly right because the symmetry of this thing is looking funky. We tend to just call these things multiplets, and they arise ultimately because you are splitting the peaks with inequivalent hydrogens, right? So instead of splitting this exactly 50-50, now this is more like a 60-30 or 70-30, 60-40 type of approach, depending on what the values of the coupling constants may be. We're going to investigate that a little bit in more detail. But in addition to that, of course, now the green hydrogen is next to a carbon with two H's, so that will also be split into triplets. So here, not only will you have your ethyl group split up into triplet and multiplet, but then you'll also have the peak, of course, of the other carbon H that you have present in there. All right, but generally speaking, you're expecting to see triplet quartet or triplet multiplet if there is an ethyl group present. Now, in the case of an isopropyl group, well, the CH3 groups are actually equivalent with each other because via rotation they can exchange places. So you have 6 hydrogens that are pretty much the same type of hydrogen, and then you have the pink hydrogen here, which is its separate thing. So you have two different kinds of hydrogen. So if the isopropyl group is bound to a carbon that doesn't have hydrogens, then all you will see is that the blue hydrogens, the CH3 hydrogens, are next to a carbon with an H, so they will be split into a doublet. And that doublet is going to be worth 6 hydrogens in total. Now the carbon, the pink hydrogen, right? It's bound to a carbon next to not just a CH3, but rather two CH3. So you're bound next to 6 equivalent hydrogens. So what that's going to do is split up your signal into a septet. And if you follow Pascal's triangle, you're going to get the overall number right here. And you can see that the first peak is 1. Then you go 1 to 1. Then this becomes 1, 2 to 1. Then 1, 3, 3, 1. 1, 4, 6, 4, 1. And in case you're wondering how Pascal's triangle works, it's simply the value in the middle is the sum of the values on top. So if you look at this 4 down here, well, the 4 is basically the 1 plus the 3. The 6 right here is the 3 plus the 3. 4 is 3 plus 1, and then 1, right? The extremes are always 1s, but the middles you have to adapt the values above it to come up with this number. So when you get to the very bottom, after you do the splitting, a total of 6 times, you end up with 1 plus 4 is 5, 4 plus 6 is 10, right? So you end up with a 1 to 5 to 10 to 10 to 5 to 1 ratio for this peak. And the other thing too is that because this is only worth 1 hydrogen, which is the pink hydrogen, this is going to be a very small signal compared to this one. So this one will be very tall, and this will be kind of small, but you will see that it basically kind of creates that, septet looking type of signal. Now, if the isopropyl group is bound to carbon that has hydrogens, then this will become most likely not a multiplet, but it will still look somewhat like this. You'll be able to tell by the fact that it's small in height and the fact that it has a lot of peaks, that's probably going to be that methine CH signal. All right, now that brings us to terbutyl. Now, terbutyl is an interesting group because you have 3 CH3 groups which are all equivalent to each other via rotation. But each one of those CH3 groups is bound to a carbon that doesn't contain necessarily a hydrogen, so long as this carbon is bound to some other carbon, right? Because if this was just isobutane, then this will contain a hydrogen and you will split up all those signals. But if the t-butyl group is bound to another carbon, then this carbon contains no hydrogens. And so all you will get is simply a singlet. But this singlet is going to integrate to a total of 9. So whenever you see that your integration is coming up with multiples of 9. So if this signal integrates to 9 protons, 18, 27, then you have 1 or 2 or 3 t-butyl groups present respectively. All equivalent, of course, because if they were not equivalent, they will not be the same peak. You'll have different peaks for inequivalent groups. But this is, kind of nice to see. And then for your methyl groups, those are multiples of 3. So you also have to be on the lookout for that, because you could potentially have 3 separate methyl groups which happen to be equivalent but are not part of a t-butyl functionality. That will still give you a singlet with 9 proton as the integration. So that's the only thing to be on the lookout for. But those cases, in my opinion, are kind of rare. And most likely than not, an integration of 9 or in multiples of 9 is going to be very indicative of having a t-butyl group. So be on the lookout for all of those signals, all of those type of patterns, because it will kind of expedite the process of figuring out what you have present, because you can look at that doublet and a multiplet, an integration of 6 to 1, roughly speaking, boom, you'll say isopropyl automatically. If you see a singlet, that integrates to 9 or 18, 27, then you say t-butyl, 2 t-butyls, 3 t-butyls. If you have a triplet with a quartet, or a triplet with a slight multiplet, but the integration is 3 to 2, you probably have an ethyl group present. And those are the things that you have to be on the lookout for when looking at your NMR spectrum. Okay, in the next video, we are going to now look a little bit more in detail at this J coupling constant value and see how we can use the coupling constant values to figure out which signal corresponds to what kind of proton. So I'll see you in the next video.